So let's talk about an example here. Let me plug in some data from the slides. Here's a set of p-chart data that I generated artificially. So these are data for a sample size, a large sample size of 400. And as a matter of fact, I generated these data using a process fraction nonconforming of 3%. That's true, as a matter of fact, except at sample 9, where I cheated and did something else. But the other 19 of these x's are binomial variables, or realizations of binomial variables with n of 400, p of 0.03, and that's what's in these x rows here. The p hat rows are, of course, the x's over 400. Now, the question is, if I was faced with this sequence of values p hat, I had this as my process standard. I knew that in the past the process had turned out 3% non-conforming. I wish to extend that into the, or I wish to apply that to these p hats as they roll in. What about control limits? Well, using the standard p of 0.03, my lower control limit for p hat will be 0.03 minus 3 square roots of 0.03 times 0.97, 0.97 being 1 minus 0.03 over the sample size, and the sample size here is 400. As a matter of fact, there are 20 samples, but that's not relevant. What's relevant is how many items were inspected to find 15 non-conforming items at period 1. How many items were inspected to find 11 non-conforming items at period 2, and so on. You can check my arithmetic. That lower control limit, I believe, turns out to be 0.0044. The units there are non-conforming items, or items non-conforming per inspection. So it's a fraction non-conforming. The upper control limit for p hat is that same thing with a plus sign in there, and that turns out to be 0.0556. And the point is that one applies this and this to the p hat values in this table as they come rolling in, and what one finds is that only sample 9, where I cheated and did something other than binomial with n of 400, p of 0.03 to make the simulated data, only sample 9 produces a point that plots out of control. That is this value up here, exceeds that upper control limit. Okay, so let me show you what a jump control chart for this example looks like. Here is the center line, there's the upper control limit, there's the lower control limit, and there are the p-hat values plotted against time or against sample number, and it's only at sample 9 that we get a point that plots outside of control limits. So what that picture tells us is that at time 9, at period 9, there's an indication that indeed P of 0.03 was not operating at that period. That is, as the data roll in at the 9th sample, the alarm bell would ring and I would be warned that there's been a process change away from the standard value of P being 0.03.